Thanks, Heiko. Now let's get started. Machine vision gives eyes to computer systems. I'm sure you've all heard that before, but it's true. It's a cornerstone of modern automation, and the field's continuing to evolve at a rapid pace. Machine vision technologies are setting new benchmarks for efficiency and precision through innovations like event-based imaging and machine learning or AI, and are taking advantage of generational improvements in processing power. In this talk today, we'll explore current trends in machine vision, highlighting some breakthroughs in event-based imaging, industrial streaming cameras, area scan sensors, AI-driven software, and their practical applications. Now, starting off with event-based, this represents one of the most disruptive innovations in machine vision since AI entered the field. These image sensors are neuromorphic in their design. They mimic our retina. Our retina reacts to changes in light intensity, ignoring areas without change. And then our neurons process this data into what we recognize as an image by effectively integrating these changes in light over time. As my colleague Rob will show here, event-based sensors provide information on movement only, making this movement critical for functionality. By contrast, frame-based cameras capture entire scenes, regardless of what your application is actually interested in. Now, since they're not constantly sending dense image data across their output, event sensors demand far less bandwidth, similar to how compressed video only updates altered pixels. Each pixel of the sensor operates independently as a contrast change detector, similar to a photoreceptor in our eyes. The light comes in, hits a diode, and that diode creates a photocurrent. Then that photocurrent is put into a logarithmic converter, and a voltage is output. This resulting voltage is compared to a threshold, and if it exceeds that threshold, an event is fired, and we get information from that pixel. Due to this design, event-based cameras can do changes in a variety of light levels. They don't use the concept of an exposure time in this pixel design. This leads to a high dynamic range. It's estimated at about 120 decibels, whereas kind of more traditional silicon sensors near like 70 dB at most. That vastly outperforms their frame-based counterparts. An event-based camera also offers the necessary performance for capturing fast-moving objects without loss of information. This is nearly unavoidable with image-based sensors due to fixed frame rates. Even a camera with 1,000 frames per second captures frames only every 1,000 microseconds. And not to mention, you'll now need to flood the scene with light due to the very quick exposure time. The temporal resolution, or the minimum measurable time difference between two successive changes in brightness events, can be less than 100 microseconds on an event-based sensor. Here's an example of event-based imaging potential in high-speed quality control. If you consider a conveyor belt carrying small components at high velocity, traditional cameras might struggle to capture details due to motion blur or limited frame rate. Even a specialized technology like line scan sensors would complicate the setup with timings and powerful required lighting. Event-based cameras can detect and analyze rapid changes in position or appearance, identifying defects in real time. In guidance applications, these cameras can enable precise movement tracking, helping robots or autonomous platforms adapt to dynamic environments. IDS currently offers a single event-based sensor, the IMX636. But this is kind of like the highest performance and highest resolution sensor from Prophecy. Again, the big deal here is you can observe motion without any sort of gaps. There's low latency, and the camera itself has really high dynamic range, all while being very efficient bandwidth-wise. And this sensor is in our X family lineup in the XCP and XLE. And if you end up finding that this high-end sensor, might be too much performance for your application, we can easily swap to other variants provided by Prophecy and Sony. Now onto industrial streaming cameras. These blend the functionality of industrial machine vision cameras, security or IP cameras, and webcams. They epitomize Industry 4.0's shift from centralized processing to interconnected smart devices. While industrial machine vision cameras require a host PC, security cameras function as Internet of Things devices, streaming video data over networks without needing a dedicated PC. And this ease of setup is invaluable in many applications. These cameras also inherit the robustness of industrial components, featuring long-term availability, durable housing, and flexible lensing options. Unlike security cameras with fixed wide field of view lenses, industrial streaming cameras support interchangeable lenses, accommodating various fields of view and specialized needs. Their dashcam-like ability to record video on board ensures errors are captured even if detected later on in the process. For example, a factory might use these cameras to monitor bottlenecks in production lines, and if a defect is discovered downstream, the recorded footage allows engineers to trace the error's origin. Another compelling application is remote monitoring. Industrial streaming cameras can be deployed in harsh environments such as mines or offshore rigs where human presence is limited or is very dangerous. Their ability to stream high-quality video to control centers ensures real-time monitoring and quick response times to any detected anomalies. IDS offers housed streaming cameras with an SCP, a flexible board level option with the SLE, and a more powerful platform with embedded AI in the Malibu. Now, even old traditional area scan sensors continue to advance with an increase in overall image performance as their technology continues to innovate. And today we're going to highlight Sony's Starvis 2 sensors. They're relatively interesting. Um, they're the latest rolling shutter sensors that improved their pixel geometry from their previous generation. These updated pixels enhance sensitivity and reduce noise while maintaining their cost-effective nature. Now, in particular, Starvis's two wider photodiodes and improved fill factor boost performance in the near-infrared wavelengths of about 750 to 1000 nanometers. These are critical wavelengths for low light applications and can be used in specific inspections, revealing details that aren't visible with visible light. In the food industry, near-infrared imaging can detect foreign objects or impurities in products like grains or packaged foods. Similarly, in the semiconductor industry, these sensors can reveal structural inconsistencies in wafers, ensuring higher yields and fewer defects in the process. By offering a cost-effective alternative to dedicated shortwave infrared sensors, Starvis 2 enables broader adoption of advanced imaging in industries with tighter budgeting constraints. The Starvis 2 sensors are available in our XCP and XLS, and they're slowly rolling out into our new Gigi LE family. Currently, the 2 megapixel version is available there. We have up to 12 megapixel resolution sensors in the XCP and XLE. And we have both color and monochrome, so you can take advantage of a special advantage of that near infrared sensitivity with the monochrome versions. Now, onto a hot topic that's been hot for quite a long time now, AI. So the software trends in machine vision still remain pretty dominated by deep learning and AI. AI does excel in many applications, but it's not an answer to every question. Deep learning relies on vast data sets to identify relevant image features for specific tasks, and data collection and labeling can be time intensive. For some tasks, rules-based image processing and leveraging the expertise of skilled engineers still remains more efficient. Still, some advancements like synthetic training data and sophisticated assistance algorithms in the labeling process are streamlining the overall adoption of AI. Synthetic data mitigates those challenges of data collection and labeling by using simulations like this to generate labeled images. These simulations, which are rooted in rendering tools and ray tracing, kind of align with the broader trend of digital twins in manufacturing. A manufacturer could simulate various lighting conditions and object orientations to train a network capable of identifying defects in automotive components, reducing reliance on getting many of those physical examples, especially when you have a very high acceptance rates already. Pre-trained networks provide out-of-the-box solutions for common tasks like person detection, optical character recognition, and defect detection. Fine-tuning these networks with application-specific data often requires significantly less effort than training from scratch. The labeling process becomes even easier with assistive algorithms for this labor-intensive portion of the solution. For example, a factory producing glass panels might start with a pre-trained network for surface anomaly detection, then adapt it to identify scratches or cracks specific to their product line. IDS has some offerings in both software and hardware that run AI algorithms. The Malibu and the Rio and Rome are hardware offerings. The Malibu's claim to fame is it uses a ISP from Ambarella, and that allows us to do really fast CNN processing on board there and gives the option of doing RTSP streaming as well. The Rio and Rome came before it. They're FPGA based, and this means they have much more precise timing and global shutter options for more industrial applications that require precise triggering. And the Rio and Rome also have OPC UA compliance for better factory automation um, integration into um, controllers. And lastly, paired with these is our cloud training platform, Lighthouse. This is where you'd upload your data sets, label them, do the training, and you can also create what we call vision apps based on Google Blockly in our block-based editor. And there's even a little wizard to help you through which types of networks to start with. Now on to some examples. Let's go back to event-based here and consider the task of counting objects. This is a really common machine vision application. Event-based cameras excel in counting fast-moving items such as cascading parts, and their fine temporal resolution allows precise tracking of moving objects by detecting transitions pixel by pixel. Image-based cameras can struggle in such scenarios, where objects may skip across multiple pixels between frames, or even during a frame, leading to motion blur. A pharmaceutical company might use an event-based camera to count pills dispensed into bottles, ensuring accuracy at very high speeds. For stationary objects, area scan cameras are more suitable, of course. If we take the deep learning approach, we'll be able to handle challenging environments with varied backgrounds and object positions. But typical networks fail to provide quantitative information, like exact dimensions. An electronics manufacturer might use a neural network to detect presence absence of parts, but would fall back to a more traditional rules-based approach to provide precise measurements for those parts. Shortwave infrared imaging often reveals features completely invisible under standard lighting by exploiting material-specific interactions. Determining the optimal wavelength for highlighting these features is crucial. And if that required wavelength is less than 1,000 nanometers, you could use a Starvis 2 sensor instead to provide a cost-effective alternative. In agriculture, near-infrared imaging can assess crop health by detecting water stress or pest damage. In plastics recycling, it can differentiate between types of polymers based on their spectral signatures, streamlining a sorting process. These applications highlight the versatility of near-infrared imaging in addressing diverse industrial challenges. So sometimes there is no need to go to a much more expensive shortwave infrared sensor. Surface inspection is another area where machine vision technologies shine. Event-based cameras can detect minute vibrations or deformations on surfaces in real time, aiding industries like aerospace where material integrity is absolutely critical. AI-powered algorithms can further enhance these inspections by identifying subtle patterns indicative of wear or damage, reducing the downtime and preventing any failures. The evolution of machine vision is helping driving manufacturers' digital transformation. These advancing technologies of sensors, hardware platforms, software, and AI are empowering manufacturers to optimize quality assurance and process improvements. And I do hope this talk opened your eyes to some new movements in machine vision space and maybe spark some inspiration on how you'll solve the problems that you're faced with. Thanks for listening.